Uh, okay. I'm sorry for this inconvenience. Hello, everyone. I am Xinjia Hu, and I am a PhD student from the Max Planck Institute for the Physics of Complex Systems. And my talk today is using climate factors to estimate flood economic loss risk. And please to the next slide. Thank you. First, I will briefly introduce the background of this research. And as we know, the large-scale climate factors such as El Niño source oscillation are very important drivers of spatial and temporal change in hydrometeorological variables and can influence extreme precipitation in remote regions, and which is called the teleconnection. And it can cause severe natural disasters such as flooding, and which can lead to severe damages. And so such factors can cause influence concurrently or in a delayed way. So it is useful for decision makers to consider this lagged impact of climate factors on societal risks, and which are caused by these extreme weather events such as extreme precipitation. So it means that we can use these factors to estimate the extreme weather related economic loss. So this is the basic idea of this research. So please come to the next slide. Thank you. And in this study, we mainly put forward a framework to connect these climate factors with flood economic loss and through precipitation variation as a connecting bridge. And this is the method framework we used in this study. And the steps include the first, it is to analyze the spatial distribution and temporal variation of precipitation anomalies during flood season and extract the main patterns of rainfall. And then we construct a predictor pool based on precipitation-related oceanic and atmospheric variables. And then we build the prediction model of precipitation with different predictors and evaluate the skew of the prediction model. And then we divide the flood economic loss data set into different groups based on precipitation patterns and simulate the corresponding loss events in each group and evaluate the economic loss risk caused by the flood events in each group. And I will introduce in details of every part in next few slides. And please to the next one. We apply our method framework to a case study and to see how our framework works. And we use one province from China as an example. And the study region we selected is Hunan province, and which locates in the middle reaches of the Yangtze River region and affected by the East Asia summer monsoon and receives sufficient rain in flood season. And we choose this region also because it is the important agricultural and commodity grain base in China. And also because the flood-related economic loss data is available in this region, because this kind of data is not always that accessible in some way. And the precipitation data we use is a C2 observational data set. And we take the period from April to August as the flood season, and which we can see that the precipitation and flood frequency mainly are concentrated during this period from figure 3. And to the next slide, please. I just mentioned from the framework part that the spatial distribution and temporal variation of precipitation act as a bridge to connect the climate factors and economic laws. So first, we apply the EOF analysis to precipitation in flood season and extract the main modes of it. And the spatial pattern and the time coefficient of EOF are used as the classification criteria of disaster dataset. And so for Hunan province, the main spatial mode are uniformly distributed as a EOF1 and north-south opposite trend as a EOF2. And for each spatial mode, we use the value of PC to separate the whole period as the rainy years, normal years, and dry years. And so this is the first step of our framework. And please to the next slide. And the PC value of precipitation is an important classification criteria of the economic loss dataset and can act as the connecting bridge here. So we need to use climate factors to make a prediction of these PC's values. And we use stepwise regression method to predict PCs of precipitation. And first, we apply the cross-correlation analysis and to identify the correlated climate factors. And as you know, the Hunan province is located in a region that is influenced by the southeastern and southwestern monsoon in flood season. So it may suffer from large floods if sea surface temperature and atmospheric conditions are anomalous. So we consider the oceanic and atmospheric circulation anomalies as predictors, and 4 kinds of factors are taken into account, and which are the global sea surface temperature, the sea level pressure field, and the general atmospheric and oceanic circulation indices, and 500 hectopascal height field. And we finally selected the highly correlated climate factors for the time coefficient of precipitation in each mode for the bidirectional stepwise variable selection step. And these factors we consider are listed in table 2. And then in order to examine whether the regression model is generalized beyond the sample data and avoid overweight fitting, we use the leave one out cross-validation as the retrospective forecast. And the correlation score for both predict PCs with its observational value are very high in this study, as we can see from figure 6. And these are the predicted PC compared with the observational value that the predicted value we obtained from the stepwise regression model. And please come to the next slide. And and considering that the dataset events in the dataset, the disaster events in the dataset are limited from we used. It's just from 1984 to 2007, so it's not a quite large dataset. So we use a Monte Carlo simulation to simulate a 1,000-year flood loss events for the rainy years groups, the dry year groups, and normal year groups under different precipitation patterns, and obtain the AEP and OEP curves. And this figure 7 shows that under the same exceedance probability, the loss in rainy years is more serious, followed by the normal years, and the lightest loss is in the dry years. And from the figure 8, we can see that under different return periods, both the maximum loss in one flood event and the annual accumulated loss are largest when the year is rainy. And additionally, the maximum loss and the annual accumulated loss are quite close to each other under very extreme conditions, which means that the return period is 1,000 years. And so please to the next slide. As the spatial pattern of the EOF2 is north-south opposite trend, so we estimate the flood risk for the northern and southern areas of Hunan province separately. And so from the right figure, this right one, we can see that the spatial distribution of the precipitation pattern is roughly separated by the 27.5 north degree. So this is act as the dividing line, and we divide the area based on this line to two parts, and use the Monte Carlo simulation steps to obtain this exceedance probability curves again. And we have an interesting finding when we make a comparison of these two parts of the province. And so please to the next slide. Thank you. Yeah, and this is the comparison of the results obtained from the both parts of the province. And we find from the figure 10 that in terms of the expected maximum loss, and when less serious flooding occurs, so it means that with the smaller return period, there is a very little difference between these two areas. But in case of the catastrophes, that means that is in larger return period, the related economic loss are much larger in the southern area than in the northern area. And please to the next slide. And this figure shows that the result of the annual accumulated loss, which is the opposite of the maximum loss. And the southern region, we can see that it suffers more serious maximum loss under the very extreme condition. That means in larger return period. And the annual accumulated loss is generally larger in the northern part. And so we can conclude that the southern area in Hunan province tends to suffer more losses in a certain flood event. And maybe the potential reason is due to its possibly weaker disaster management measures, and whereas in the northern area, the accumulated economic loss is more serious. And the interesting thing is that inside Hunan province, the northern region and the southern region, they are in some ways exist some imbalance of the economic development. And so please to the final slide. So the conclusion of this study is that we propose the framework to connect the climate factors and flood economic loss risk based on the spatial distribution and temperature variation of flood season precipitation, and the estimated annual accumulated economic loss and maximum loss are more serious in rainy years, and it's followed by normal years and dry years. And the annual average loss can be obtained by calculating the area of AEP curves, and we can estimate the economic loss on the different return period, as you can see from some figures. And there is an obvious difference in flood risk between the northern area and southern area in Hunan, and the economic development, level of risk management, frequency of extreme weather events may be the reasons leading to this result. But there still exists some limitation of this study. And the limitation first is that the relationship we considered between the PCs of the precipitation and climate factors is based on the historical data sets. So this relationship is relatively stationary. So we cannot consider that the changing relationship between the precipitation and the climate factors. So this is one of the limitations. Another is that our framework can estimate flood risk severe months in advance, and it can be used as an early warning tool. and but it's very difficult to benchmark the estimated risk result, and this is the another limitation of this study. So that is all about the research. I'm very looking forward to some questions. Thank you.